So what this talks about basically is not only exploiting the heap in double freeze, but doing it in a way that is, we don't traditionally think of the heap that way. We normally think of the heap in a manner that's very linear and very buffer overflow style, buffer overflow-esque. So what I'm hoping to do is get everybody thinking a little bit differently and kind of think about the fringe cases a little bit more, because like it or not, that's kind of the way the world's going. I've got a lot of slides. I had to cut a little bit out of the slides, out of the content, so I apologize to you, and I'm going to have to talk fast. Real basically, the heap, it's just a globally scoped data structure. It's persistent. It's for dynamically allocated memory that exists until you free it. It kind of works like the stack. It's similar in that scope, except for the fact that it's not local to a function. As I said, it exists until free. The glibc implementation was originally written by Doug Lee. That's the one that most everyone's familiar with. It's been revamped by Wolfram Glogger, and it's called ptmalloc 2. It's a slight variant. There's not a lot of huge differences there. The biggest two being multiple heaps and arenas are supported, and the support for threads. What I worked on with this was glibc 2.4. That was what's current at the time. I looked last night, and glibc 2.6 was the current, and I pulled it down and took a look at it, and everything was pretty much the same. So not a whole lot had changed there. As I said, the multiple heaps are supported, so the heap's a little bit of a misnomer. Something that the Unix world isn't so much used to, but something that's fairly common in the Windows world. Heaps normally allocated either traditionally via sbreak, which extends the data segment, but glibc, if it has mmap, then it will actually prefer to use that and let the operating system deal with how it's done. Allocation requests are filled either from the top chunk or from free lists, and I'm going to get into those a little bit in 4 or 5 slides or so. Allocated chunks are navigated by its size, whereas free chunks are navigated by the linked list, and adjacent free blocks will be coalesced into a single one, so that implies that no 2 free blocks will ever be adjacent to each other. As far as the data structures, every heap starts off with a heap info structure, followed by a malloc state structure. The heap info structure isn't used a whole lot. In fact, I think off the top of my head that it's only referenced once throughout the entire glibc code. Most everything that deals with navigating the heap is done through the malloc state structure, which is what defines the arena. And then, of course, any number of malloc chunk structures, which are the ones that pretty much everyone's familiar with. Heap info structure it defines the size of the heap, pointer to the arena, and pointer to the previous heap if one exists. The malloc state structure is a little bit more interesting. It has the mutual exclusions that allow for multi-threaded and async safe or async mostly safe code using malloc. Flags indicating the status, whether the heap is contiguous or not, so on and so forth. And then, of course, arrays of pointers to malloc chunks, which are fast binned in normal size chunks, and then pointers to the next malloc state structure. The malloc state structure, or the malloc chunk, contains the size of the previous adjacent chunk, size of the current chunk, and then if free, there's a pointer to the next free block in the previous free block. Pretty much everyone's probably going to be familiar with that in here. There's the structure of it. It's probably the most well-known data structure in the heap. It's semi-universal. Pretty important point, especially when dealing with double freeze, is that malloc chunks have 2 different representations, even though they contain the same physical data structure. An allocated block of memory kind of goes like this. It's the size of the previous chunk, size of the current chunk. Then we've got 3 flags. A lot of the documentation, even the documentation in the source code is currently wrong. There's 3 flags there for previous in use, whether the chunk is mem-mapped, and then if it's in a non-main arena. Free chunks, same physical structure, except where there used to be just a pointer to user data, there's now the two pointers to the previous and the prior chunk in the linked list, and of course the ismit mmapped flag is gone. Chunks that are mem-mapped just get mem-unmapped, so there's no reason for them to ever be in a free list. Free blocks get stuck into bins, which is basically the same thing as a free list. It's just the glibc term for it. There's two different types of free list, fast bins and normal bins. The fast bins are basically some of the checks are skipped on them. They're not coalesced. They're not sorted. Whereas the normal size chunks, depending on what size, they have two different sizes of normal size chunks. One that's the smaller ones and the larger ones, and they're sorted a little bit differently. Normal size bins split into three basic categories. The first bin is the unsorted bin. It's been talked about in a couple different papers as far as buffer overflows and things and exploiting that. The small normal bin chunks are the small normal chunk bins, and the large ones. Larger requests get serviced via memmap, and like I said, there's really no bin form, there's no purpose. It gets just unmapped. Fast bins, they're removed in a LIFO manner. That actually gives us a lot of control. Blocks that we free, we can immediately get right back if necessary. The range from 0 to 80 bytes, anything larger than that falls into a normal size bin, with the default size, the default max size being 64 bytes. And then there's a table there with the what chunk sizes get stored in there and into the various bins. Normal bins, as I said, contain the same physical structure as a fast bin. Blocks of less than 512 bytes fall into the small bin range. They're also not sorted, and it's actually possible for fast bin chunks to get coalesced at a certain point when allocating other memories, and under certain conditions, malloc consolidate will get called in and actually consolidate fast bins. So there's a little bit of overlap there, but it makes sense when you actually look at it and think about it for a minute. Chunks larger than 512 bytes and less than 128K fall into the normal size bin. They get sorted in the smallest descending order, and they get pulled out in FIFO order, which isn't really conducive to what we'd like. So the fast bins and the small normal size bins are kind of better targets because we yield better control over them. In addition to that, we have two special chunks. We have the top chunk and the last remainder chunk. Neither one of those are ever in any bin. The top chunk borders the end of memory. It's used for allocation if possible. If there's nothing, like if a request comes in and you can't fill it out of one of the free lists, then it tries to take it out of the top chunk. If that fails, then it'll try to extend the top chunk. And if that fails, then it'll try to create a new arena and create a new heap. When a chunk that's getting freed borders the top chunk, it gets folded back into it, and it becomes the top chunk essentially. Inside of the code base, it's treated like it always exists, and therefore it's treated a little bit special, and it can grow and shrink as well, obviously. The last remainder is the result of allocation request that's smaller than any of the size chunks. When it gets split, and what's left of that gets pointed to by the last remainder chunk, or becomes the last remainder chunk. Just a quick few notes on heap operations. When you create a heap, it's created implicitly. It's not like Windows. You can't call heap create or anything like that. And when you not even sure what I was trying to say there. When you allocate a block, fast blocks or fast bin blocks can't cause consolidation small normal size ones can cause it under certain circumstances, and large normal ones always call that, which is something we're going to exploit and use to our advantage a little bit later. When resizing a chunk, one of the most important things for us to be aware of is that it can actually cause our chunk to be freed, which may or may not be what we want depending on the situation. And then when freeing chunks, it can also cause trigger consolidation, and can actually cause the heap to be resized, which in turn can cause problems for us. Moving into the subject matter, what we're looking at is double freeze. They're an instance of dangling pointers you use after free. They've been known about for a while. There's nothing really extraordinary about them other than they're kind of providing interesting insight into the way that the heap works. In the example there, basically we have two calls to free with the same pointer, and it's obviously invalid. And double freeze have surprisingly not really been talked about a whole lot. When I looked at the Voodoo malloc tricks and Once Upon a Free papers, which were the kind of the original heap exploitation papers, there was nothing in there. Advanced Dougley's malloc exploits mentions them, but it's it's in passing. The malloc Maleficarium mentions it, but they actually it's in a glibc string, so they don't even actually mention it. It's just from a copy of some code that they put in there. The Shellcoder's Handbook has a single paragraph far down into the book. It tells you a little bit about them, that they're not really exploitable, that most systems have protections against them. It doesn't happen a whole lot, but if you do see that they're not setting the pointer to null after freeing it, that you should probably look for them. However, the Art of Software Security Assessment, which just came out not too long ago, did talk about it a little bit. And they, in the single sentence there, kind of summarized the problem in saying that if memory is reused between successive calls to freeze, the memory block could be entered into the free list twice, which is kind of the crux of the problem in most instances. In traditional double free exploitation, there's only been one talk that I could really find, and it was a post to a mailing list that dealt with an exploit for the CVS server bug that came out in 2003. It was actually it was the only thing that I can find that actually talked about exploiting them, whereas everything else either just mentioned them in passing or just didn't mention them at all. The biggest thing to remember here, though, is that two different chunks can exist, or the same chunk can exist in two different places and contain two different states at the same time. As you can see there's the representation of the two of them again, just for your memory. What happens when you free a chunk the first time is that your chunk ends up in the free list, which gets linked in. You have a forward and a backwards pointer. The gray chunk is our chunk, obviously. Now, if you think about it, if you called free again, it's kind of curious what could happen. You'd end up with it in the list twice. So if you got it allocated back, it would still be in the free list. It would exist in both places at the same time, which is what I tried to depict in this image, but it was kind of hard to do in a manner that could actually be shown halfway decently. Basically, the problem is that when